record. Now I should do a share screen. Oh, yes, yes, share. Do you see my screen?
Yes, we can see.
Okay, very good. So we're still dealing with how to describe physics in curved spaces, and specifically, let me just organize a little bit my stuff here. And specifically, how to describe vectors and tensors in curved space-time. So last time we had a very lengthy discussion with the final goal. This is the point to remember, is that in any curved space, or the technical term is a manifold, I identify vectors as directional derivatives. That's the most important thing, right? So we define what is a manifold, which is any curved space which is well behaved. Something that locally looks like Euclidean, although globally it is not. So not something, you can think of any spaces. Mathematicians have great imagination. What we do here in the physics, right? We're thinking of general spaces, but they're well behaved. We're limiting ourselves to something that looks reasonable, in the sense that if you look close enough, it looks flat, right? And then we said that because of this property of a manifold, we can always locally find a coordinate system next to any point P, right, in the closest vicinity of P. And we can always find curves that go along this space that pass through this point P. And then we can always find this curve really defines basically a functional, right, which changing any function f to the f d lambda. So essentially, what we wrote down is that basically, right, maybe I can just plot it down, right? So we have some sort of a manifold M, and we put a curve at point P, and we just think of a curve lambda or gamma, I call this curve, which is specified by some parameter lambda, so it's a parameterized curve, right? And this parameterized curve through P defines a directional derivative, which is basically a generalization of the concept of partial derivative. So in partial derivative, right, we have a set of coordinates, we keep all the coordinates fixed, and we just change one coordinate. And we see how the function changes as we change this one coordinate, and we call this a partial derivative of the function f. So here we have a directional derivative, namely, we're not selecting a coordinate, but we're selecting a curve, and we're looking how a function f changes from the point P, right, to another point next to it along this curve, lambda, right? And we found out that the f over the lambda, right, is just dx mu over the lambda over the df over dx mu, where dx mu was something which we put in as coordinates in the vicinity of P, just to keep our life simple. And as we said, we can always do that. And since this is true for any function f, essentially we could write down the vector as d over d lambda. Which kind of makes sense, because when we put some coordinates, we can use them as a basis to this to any vector lambda. So the bottom line is that d over d lambda defines a vector. All right. And of course, it transforms the same way as we're used to from special relativity. Right? So we can think of it as being composed of some basis, right? Again, d mu, which is somewhat arbitrary. So if we found a basis was the over d mu, just d mu, right? Or call it the mu. So it's just generalization of what we did in flat space time to curved spaces. This is this is called a coordinate basis. This is quite general. I mean, I didn't even ask the coordinates to be orthogonal to each other. I just said, look, I'm just specifying a set of n coordinates, basically on the manifold. It doesn't have to be, basically, it doesn't have to be orthonormal basis, just any basis. So that's why it's called a coordinate basis. Right, and then we say that any vector, the same way as we adopted from special relativity, any vector does not depend on the coordinate, right? So any vector, the vector is independent on the coordinates, right? So that means that any vector v I can write as the components v mu, d mu, right? Again, this is the component, and this is the direction, basically. Then, of course, the transformation law of the contravariant vector would be v mu prime is just dx mu prime over dx mu v mu. So the transformation law of contravariant vector. Really of the components of a contravariant vector, but since we're not going to use really the basis, then we simply call it transformation law of the contravariant vector. Right? Okay, so this is just now, of course, we had the covariant vector. So if we said that the basis for a contravariant vector is a d over d lambda, then the basis for covariant vectors would just be the gradient, the dx mu. The covariant vectors. Right. Again, it's the same idea that we had previously. We think of covariant vectors as a linear mapping from TP to R, right? From omega is a mapping from TP to R. So these are abstract objects which take a contravariant vector and map it into some number R. Again, similar to the simplest way to think of it is possibly a row vector versus column vector. So obviously the canonical example, these are also called one forms. One forms, the canonical example being the gradient of a function df. Right, and again, the gradient of the coordinate functions provide a natural basis for this cotangle space. Natural cotangle space, right, is the gradient of the coordinate function. x mu, right? And obviously dx mu, right, that operates on a vector d nu, just equal to dx mu over dx nu, which is just delta mu. Right, so we choose the gradients, so the set of all gradients of the coordinates we choose as a basis of the one forms. So the sets. Is appropriate for a basis of the one forms. But basically, any one form we can always write omega is just omega mu dx. This is really what we do is a generalization of what we did in special relativity, but now this is something which is true at any arbitrarily curved space. Importantly, it doesn't really even have to be linear. Okay? In special relativity, everything was linear, now it is not necessarily. Okay, and then the generalization for tensors were pretty straightforward, right? So for tensors, right, again, KL tensor, just writing T as the component, right? T mu 1, mu K, mu 1, mu L, and then just the coordinates, which would now be d mu 1, external derivative, d mu K, external derivative, dx mu 1, dx mu K, or L, sorry. This is the symbol I use for external derivative. Outer product or tensor product, sometimes it's called wedge product, is something which is slightly different. And when we do it like that, then the transformation laws of the component of T is exactly what we'd expect them to be. Right? Transformation laws. T mu 1 prime, mu K prime, mu 1 prime, mu L prime is just dx mu 1 prime over dx mu 1, dx mu K prime over dx mu K. And then for the lower indices, of course, it's the opposite, dx mu 1 over dx mu 1 prime, dx mu L over dx mu L prime, right, and then times t mu 1 mu K, mu 1 mu L. There's really nothing else that can be done here. So this is the transformation law of the tensor components. Right? Then I gave an example, and the example is pretty much what you know. The only thing it's straightforward. It's the only thing that you do. Because there's nothing else that you can do. Really, this is what you've intuitively been doing when you've been asked to transform bases from one basis to another, right? From xy to x prime y prime, right? Xy to r and theta. That's exactly what you've been doing. I've just said it in a straightforward manner. And then the last thing I had time to discuss was volume element, or invariant volume element. Wait. We want to get a volume element that is not depending on the specific coordinates that we're choosing. For that, we looked at the determinant of the metric tensor, right? G we define to be minus the determinant of G mu nu, right? Or the absolute value of G mu nu, or its determinant, right? The minus here is, of course, because in flat space, right, G, of course, G mu nu becomes eta mu nu, which is a minus 1, plus 1, plus 1, plus 1. So the determinant of eta mu nu in flat space is, of course, a minus 1. So that's why we add an extra minus here, right? And if we take the determinant of the transformation law of G mu nu, right? G nu prime is just dx mu over dx mu prime dx nu over dx mu prime G mu nu, right? If we're taking the determinant, G prime is just the x prime over dx minus 2g, right? And this term is called the Jacobian. Remind you from one of your second-year courses. And so we have to take the Jacobian of the transformation to the power minus 2. And so that's why G, the determinant, G is not a tensor, or not a scalar here, sorry. It's called a scalar density. So G is a scalar density of weight minus 2. Right? This is the weight. The number here is the weight. And so under a general transformation, right, the volume element always picks up a factor of the Jacobian. Right? So generally, dnx prime is dx mu prime over dx mu dnx. This I believe you've seen in one of your mathematical physics courses. And that means that the invariant volume element is invariant volume element is square root g dnx. Right, so again, we gave you a simple example of specifying flat space-time using spherical coordinates. The spherical coordinates would be the r, the theta, the phi. But of course, an invariant volume element is not just the r, the theta, the phi, but r squared sine theta, the r, the theta, the phi, which follows directly from this. So that's the mathematical way of generalizing things which you might have seen in previous courses now to any coordinate system that you wish. Okay, this is as far as we did last time. So before I proceed on, this is the place to stop and ask you if you have any questions. Do you have any questions? No questions? Everything is clear. Sure, everybody, everything is clear for everybody? Okay. So a few things on notation that you might find in textbooks. So if, okay, we said that the metric is in what's called canonical form. If we can write G mu nu as a diagonal with some minus ones first, then ones, and then zeros. So if we can rewrite the metric as G mu nu is just a diagonal, so minus one, could be several minuses here, and then a plus one, and then at the end zeros. This is called the canonical form. That's how it's called. Of course, if any of the eigenvalues are zero, if we have any zeros at the end, right, then of course the metric is degenerate, and then we cannot find the inverse. So we can do too much. We're not going to have that in this course, so you need not worry about this this possibility. Now, if all the signs in the metric are positive, right? So if the metric only contains the pluses here, right? Then we say that the metric is Euclidean or Riemannian, right? If all signs are plus one, we say that the metric is Euclidean or Riemannian. If there is a single minus sign, what do we call it? I think you encountered the name one day. How do we call the metric? Any guess?
Minkowski?
No. This is general. This is called pseudo-Riemannian. The metric is called pseudo-Riemannian. Another name is Lorentzian. Of course, in this course, we deal with pseudo-Riemannian metrics. What? Okay, one more thing before we can move on is talk about another tensor, which is not really a tensor, and now is the time to fix that. And that's called the Levitzivita. It really is what it really is it's a tensor density. Right. Remember that in flat space-time, right? We had the Levitzivita tensor, which we call it a tensor, but it's not really a tensor, right? We call it now a symbol, so we call it epsilon mu1 mu(n). Put it with a bar, because now it's becoming a Levitzivita symbol, which is defined as +1 if a mu1, mu2, mu(n) or even permutations of 0, 1, and -1. Right? It's a -1 if mu1, mu(n) or odd permutations. Right, of 0, 1, 2, and -1, and it's 0 otherwise. And now, the reason why it's not a tensor, but I call it a symbol, is because this is true in any coordinate system. Right? I did not specify what are the coordinates. So, that's what make it not a tensor. Now, in order to make it a tensor, what we need to do is to go back to linear algebra textbooks and realize that when we want to transfer the coordinates, then the Levitzivita symbol in the new coordinate system will get an extra factor of the determinant. So epsilon mu1 prime mu n prime is just dx mu prime over dx mu epsilon mu1 mu-n times, of course, the transformation of dx mu1 over dx mu1 prime dx mu2 dx mu2 prime dx mu-n over dx mu-n prime. You can see. Right, I'm not going to prove it to you because you can find the proof in your favorite linear algebra textbook. Just out of curiosity, have you seen this proof in any of the courses you learned? No? Okay, I don't think it's that important conceptually, but go to your favorite linear algebra textbook and you should be able to find it there. And if you really insist on that, you can ask Google where to look.
Asaf?
Yeah.
I have a question. In the beginning of the course, didn't we write M1 to Mn in the upper index?
You can do it. Just end up, okay, I put a note in here. Just end up with an extra sign. Raise and lower indices is just by a delta function. Well, by the metric here. So, okay. Okay. How do we make this a tensor? Since we like to work with tensors. If you got the idea, well, what we did previously, right? We multiply by the determinant of G to the weight over 2. So we multiply by G to the power of W over 2, right? So the result will transform like a tensor. Now, what is W here? What is the weight? What is the weight here, guys?
The number of indices? Right?
It's the power, no. What did I say is the weight?
1/2.
The weight is 1, right? It's the power in the determinant. It's just determinant to the power 1, so the weight is 1. Right? So we have to multiply by square root of the determinant of G. So to get a real tensor, we get that epsilon mu1 mu-n. Now I write it without the bar because it's not a symbol, it's a tensor. Levitzivita tensor is defined to be epsilon mu1 mu-n, is just square root of G and epsilon bar mu1 mu-n. So this whole purpose was just to pay attention when you want to make a transformation using any equation that uses the Levitzivita tensor. Have to remember to multiply by the square root of the determinant of the metric. Now, for the question that you had previously, you're right. What's your name? One who asked, but I can't read your name. Okay, doesn't matter. So if we have epsilon with upper indices, then of course numerically they are equal to the epsilon with the lower indices. But now we have a tensor density with -1, right? Because now it will be, if I use the upper indices, then I have to put here -1, right? Dx mu to dx to the power -1. So this is related to the tensor with the upper indices. So for tensors with upper indices, we have to write down epsilon mu1 mu(n), which is just the sine of g, which you have to put it on, times 1 over square root of g times epsilon mu1 mu(n). So you're going to get an extra factor of -1 essentially. Oh, I see that I put myself a note, which is going slightly beyond what we need in this course, that although epsilon, the Levitzivita tensor is a tensor, when I define it like that, using this extra factor of, when I get this extra factor of the determinant of G, in some sense, it's still not exactly a true tensor because I cannot define it globally on any manifold. There are some manifolds which I cannot define it globally. Manifolds that it can be defined are called orientable manifolds. These are the ones that we're going to work with. And non-orientable manifolds are classical one is what's called the Mobius strip. So we're not going to touch upon them in this course. Maybe if you really insist and you really love it, then I can maybe have like last week of the semester, assuming we'll do anything else by then. I can give you somewhat deeper math into more complicated, let's say, manifolds and the properties. It's more in the realm of math than the realm of physics in some sense, because physically, certainly what we have in this course is orientable manifolds. Everything is well behaved. All right. Now I think I did mention that it exists. If you're really interested, you can go to the textbook by Schutz. It's one of the recommended textbooks, and you can read about it slightly more in there. All right. Questions? No? No. No? Okay. So the next thing, it's going to be a slightly more math, but it's really mainly algebra than anything else. So the next is going to be a little bit ugly, but with a good purpose. And really it's an algebra. It's not really anything more than that. So the topic is called Covariant Derivative. Right, so unfortunately, when we said that we want to work with vectors and tensors, right? These are objects that I know how they transform. And because of the principle of general covariance, if I can write down any equation that I know is working in the absence of gravity and it conserves its form, then it will be true in arbitrary gravitational field. So that's why I insisted when we did special relativity to write down everything in terms of vectors and tensors, because vectors and tensors are well behaved. I know exactly how they transform. So I can use this principle to write down a generally covariant equation, namely an equation which will be true in arbitrary gravitational field, which is what we want. Right? We want to be able to describe physics in arbitrary curved space-time. As we say, the whole concept is that the existence of matter curves the space-time. So we want to be able to write down physics in curved space-time. Now, as you know, pretty much all interesting physics equations contain derivatives. Right? So we need to be able to work not only with vectors and tensors, but also with derivatives of vectors and tensors, right? The derivatives of the location is the velocity, the derivative of velocity is the acceleration, etc. Right? So Newton's second law of motion contains derivative. Now, unfortunately, which is really unfortunately, partial derivative of a tensor is not another tensor. This is quite bad because that means that we cannot simply use tensorial equations which contain partial derivatives as such in any arbitrary curved space-time. Right, so unfortunately, the covariant derivative, the partial derivative, of a vector tensor is not in general a new tensor. So let's say we have a vector v mu, right? So the transformation law of a vector v mu prime dx mu prime over dx mu v mu, right? Transformation law of a vector, right? We just showed that. So if you want to take a different, we want to differentiate that. So differentiate. So we can take differentiation with respect to some coordinate, right? So v mu prime over dx lambda prime, let's say, right? It is d over dx lambda prime of dx mu prime over dx mu v mu, right? So let's start with the second term first. So it's dx mu prime over dx mu. Now, v mu is defined in the old coordinate system. So I cannot take the derivative of it with respect to the new coordinate directly. The only way I can do it is to write down dx, I don't know, rho over dx lambda prime, dv mu over dx rho. Right? But then I also am left with the first part, right? So plus, again, the correct way of doing that is to write down d squared x mu prime over dx mu dx rho over dx lambda prime times v. So, you know, the reason why I wrote it like that is because this term, right, what? This term here, right, this is what we'd expect if the partial derivative was a tensor. Right? If it was a tensor, then we'd expect that dv mu prime over dx lambda prime would transform like what's written here. But we also have the second term, which we cannot just ignore. And the second term is what prevents this partial derivative to be a tensor. It's quite pity, right? Because you wrote down in one of your problem sets, right, the conservation equations, right, such as d mu t mu equal to 0, right, It's the ordinary equation. We cannot just use it as such. Cannot be used in curved spaces. So got a bit stuck. What we're really after is some way of generalizing the concept of partial derivative in a way that will reduce back to partial derivative when the space is flat, but transform like a tensor in general way, right? So that's what we're really looking for. And this object that we're looking for, and we're going to find it right now, is called the covariant derivative. Okay, so a covariant derivative right, is an operator that reduces to partial derivative in flat space but transforms like a tensor on arbitrary manifold. Okay, so we're going to construct this object right now. As I told you, we're going to do some algebra. Just a bit annoying, and there is a chance that you might cut me in some typo. You get an extra credit point at the end if you manage to do that. So pay attention. And but it's really straightforward. It's no more than much than algebra. So in order to construct that, we have to first look at the transformation law of the affine connection. So transformation law of the affine connection. Remember, we had the affine connection, gamma lambda mu mu, was defined to be b at lambda over d psi alpha, d squared psi alpha over d x mu, d x mu. Right? Psi alpha here are the locally inertial coordinate system. Now we want to change from x mu to some other coordinate system, x mu prime. So psi alpha is locally inertial coordinate system. Now we transform from x mu to x mu prime. Right? So what happens to the affine connection when we do the transformation? Gamma lambda prime mu prime is again dx lambda prime over dx alpha, d squared psi alpha over dx mu prime dx mu prime. That's the definition. So let's work it out, right? So it's just equal to, again, I want to write it down in terms of the old, in terms of the affine connection in the old coordinate system. So I write it down as dx lambda prime over dx, call it rho, right? And then dx rho over dx alpha. And then this one, just to clarify, I'm going to write it as d over dx mu prime of, again, d psi alpha over dx nu prime. I'm going to write it as d psi alpha over dx sigma, let's say, times dx sigma over dx nu prime. So dx sigma over dx nu prime times d psi alpha over dx sigma. So this is dx lambda prime over dx rho over d psi alpha times, now again I have to take the derivative here, so I have to use the two, I have two terms here. So again, I'm going to use the second term first. So it's dx sigma over dx mu prime. And then I have to take this object, d psi alpha over dx sigma, and take the derivative with respect to x mu prime. I'm not going to take the derivative of psi alpha once with respect to the old coordinate and one with respect to the new coordinate. So rather, I'm going to write it down as dx tau over dx mu prime, d squared psi alpha over dx tau dx sigma. Right. So this is the first term, and now I have the second term, which is taking this derivative here. This I can do, right? So I can have d squared x sigma over dx mu prime times d psi alpha over dx sigma. I'm sure you love it. I love it as well. Okay, so the now the nice thing is that if I look at this term here, this guy, this one plus this one, well, this is just the affine connection. So I can write it down. Gamma lambda prime mu prime is equal to dx lambda prime over dx rho. And then I have dx sigma over dx mu prime, dx tau over dx mu prime times gamma rho tau sigma plus now the second term dx lambda prime over dx rho, and then what are you going to do? Yeah, wait. Then I use here dx rho over d psi alpha, and here I have d psi alpha over dx sigma. So that's just a delta rho sigma. So since I have this delta, I can write it down as d squared x rho over d x mu prime dx mu prime. Yes. Now I can answer. Yeah.
There are voices coming from, I think, your microphone.
It should be my voice.
I think if anyone else...
I can mute myself, but I don't think we're going to have a quite hard time listening to the study. I'm not sure what to do. Right? Is this better or is it worse?
It's the same.
It's the same. I can mute all of you, but myself, if I know. I'm sure there is a way of doing it. But I want you to be able to ask questions if you want to. Okay. I'll try to speak clear, but if there's something which is not clear, then let me know. I don't have control over the internet here. Okay, you got what I wrote here, basically? I told you it's ugly, but it's just algebra. Algebraically, whatever. So again, this first term, right, this one, is what we would have gotten had the affine connection was a tensor. But we also have the second term, which we cannot ignore, which is what makes it not a tensor. Okay, But of course, this can give us some cunning idea of how to help us resolve this problem that we had with the partial derivative. In order to do that, I'm going to write this equation here in a slightly different form by using the identity. So use the identity dx lambda prime over dx rho over dx mu prime is equals to delta lambda prime mu prime. And I'm going to take the derivative of this identity. So differentiate with respect to x mu prime. And what we have is that if I take the differentiation with x mu prime, then again, the delta gives me nothing. It's just 1. So when I take the differentiation, it's 0. So I really have two terms here. So the first term would be dx lambda prime over dx rho. And then d squared x rho over dx mu prime is minus. Now I take the second term, move it to the right hand side. So now I have to take the differential of dx lambda prime. So dx lambda prime over dx rho on dx sigma, and then dx sigma over dx mu prime. And the last term is dx rho over dx mu prime. And now that here, this part is exactly what is written here. So I can use that to write down the transformation of the affine connection. Gamma lambda prime mu prime is equal to dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime times gamma rho tau sigma. I did not touch the first line. And then we have a minus what we have here, dx sigma over dx mu prime, dx rho over dx mu prime times d squared x lambda prime over dx rho dx sigma. It's ugly, but it's straightforward. Now comes the last bit. Right now I can take that, and remember I had a problem with when I tried to take the partial derivative of v. Right? This is the problem that I'm trying to solve. I want to get rid of this extra term. Now when you see the first term looks quite good, the second term is the one that is kind of preventing this to be a tensorial quantity. But now I have that, so what I'm doing now is to multiply that by v mu prime. So when I look at that, so I have gamma lambda prime mu prime times v mu prime. Right. Then this is going to be so I have all that, right? All that times v mu prime, which I can write as dx mu prime over dx kappa v kappa. right? So now I have that. And to that, I'm going to add up the equation I had for V, which is this. And go away. So I'm having that, and to that I'm adding, no. Then I'm adding this equation. And the funny part, of course, is that you're saying, or you don't see it right away, if I'm looking at the last part here, right, I have here, let's see, I have a minus x sigma, dx sigma over dx mu prime, dx rho over dx mu prime, dx mu prime over d kappa. So that gives me a delta rho kappa. All right, so these and these give me a delta rho kappa. So I can simply change this to a rho, the last term, and then I just have to switch between, maybe I should just, no, maybe I should just write it down. Properly. So from this one, just write it down. Let's not try to skip steps, just that you believe me that I'm not cheating you. So we have gamma lambda prime, mu prime, mu prime, mu prime is just, let's see. Okay. Here again, I have a delta. What did I do here? No, that's fine. No, okay. Here. Okay. This guy here and this guy here again give me a delta sigma kappa. So I'm going to write down the first term as dx lambda over lambda prime, sorry, dx lambda prime over dx rho times dx tau over dx mu prime times gamma rho tau sigma times d sigma, right, which I got from this delta sigma kappa, p kappa. I don't see my hands with delta sigma kappa. This gives me a delta sigma kappa times v kappa, so this is just v sigma. And then in the second term, I have, the second line I have minus dx sigma over dx mu prime, d squared x lambda prime over dx rho dx sigma, and 0. So this is what I get from the equation I got here. And now you can clearly see that since now I just switch notations, right? Because mu is a dummy index, rho is a dummy index, right? So instead of rho, I can write down sigma, and you wouldn't care. And instead of mu, I can write down a rho, and you wouldn't care. Right? And so these two terms will eventually cancel out. This one and this one, which will end up with d mu prime over dx lambda prime plus gamma. I think that I just change here Okay, from lambda prime I change to mu prime. Doesn't really matter. So mu prime, then wherever there is a lambda, then there is a mu. Whenever there is a mu, there is a lambda. Lambda prime, mu prime, v mu prime is just dx mu prime over dx mu, dx rho over dx lambda prime times dv mu over dx rho plus gamma mu O sigma v sigma. Okay, just to clarify that you believe me, I didn't cheat you. So every time there is here a lambda prime, I change it to a mu prime into a lambda prime. So I have a mu prime to a lambda prime, and this is a mu prime, and this is a lambda prime. So, and then rho here would become a mu. Everything I do is legal because these are just dummy indices. They appear once as an upper index and once as a lower index. And sigma here is a rho. So you immediately see that this second term just cancels out, and the first term just transforms. We have this dx mu prime over dx rho, which is just become a mu. Right? And tau here becomes a rho. Just play with that. It's quite ugly. I promise you it's going to be a little bit ugly, but it's just changing the names of these indices. So dx mu prime over dx mu, dx rho over dx lambda prime, times gamma mu rho sigma, v sigma, plus the first term I didn't touch. Which is exactly what I wanted, right? Because this guy transforms like a tensor. Right? So this leads us to define what we call the covariant derivative, which I denote with a capital lambda, so basically triangle, d lambda v mu. Another way is write v mu. If I use a comma before to define partial derivative, now it's going to be a semicolon. That's the definition. That is the notation, sorry. And the definition is exactly what is written here. It's dv mu over d lambda, but now I add this extra term. Sorry, dv mu over dx lambda, of course. Now I have this extra term, which will be gamma. Now the upper index will be the same index as in the vector mu. And we have two lower indices. So one of them would be the index in which we are deriving, so lambda, and the other one will be a dummy index, sigma multiplied by this sigma. So the equation we derived here tells us that this is a tensor, right? Because v mu prime partial derivative, covariant derivative with lambda prime, right? It transforms as dx mu prime over dx mu, dx, call it rho, over dx lambda prime, v mu covariant derivative with a rho. right? What's the rank of this tensor?
One.
1, 1, right? You can see it from the transformation laws. Okay, so essentially, again, what did I do here? I wanted to get a generalization of the form of a covariant derivative, which I can use in any arbitrarily curved space-time. So that I can use the principle of general covariance, which we discussed a few lectures ago. And I wanted something which reduces to partial derivative in the absence of gravity, namely where gamma vanishes, right, when the affine connection is 0, but that transforms like a tensor in a general coordinate transformation, and this is what I ended up with.
Asaf, could it, well, maybe it's a stupid question, but maybe I could guess it because the extra term we have in the derivative, which make it's not a tensor, it's exactly look like the affine connection, right? Like the d square, blah blah blah.
What do you mean by exactly like? We just follow through the entire algebra.
No, but in the start, you show the extra term, and it's like d square of x nu, dx nu, dx rho times.
Yes, there is. I'll discuss that. I don't know if we'll have time today, but if not, then on Sunday, I will show you that there is a more intuitive way of actually getting into that. But for the time being, just follow all the math that we did. Yes, you could have guessed it, but if you wanted to prove it, I just gave you the full proof. Right?
But I mean, maybe this is the intuition to look at the affine connection, like because it looks like this is the because you proved it to me. But how would someone think about it? Like, okay, maybe we'll try to see how the affine connection is transformed and then insert it into the derivative.
I'm not sure that if I were to ask you to derive it by yourself, you could do it easily without.
No, of course I couldn't do it, but I think But on the start, when you write the term, it's popped out. It's maybe we should look at the affine connection because of this, extra term. But no.
I'm happy that you think that it comes out naturally to you.
Okay.
And maybe I did something okay here. I don't know if it's that natural, but if it looks natural to you, then it's actually quite good. If it's so natural to you, then let me ask you the following. What about the covariant derivative of a covariant vectors, omega? Okay, so let's look at covariant vectors now. Right.
Asaf, can I ask a question, please?
Yes, you can.
So I didn't understand why the rank of it is 1 and 1, because v mu tag by itself is of rank 1, 0, right? Or 0, 1. And then why would the partial derivative change the rank of what it was?
Well, I guess you're asking for a simple way of that. No, there is a simple way, but I'm not sure I can think of it at this very moment. There is a simple way. I'm not sure that I can think of it. A derivative basically changes the rank of a tensor. It is not staying the same. I know there is a simple analogy, but at the moment, it just slipped my mind at the moment. So think of it a bit for yourself. But
this is always true.
It's always true. I mean, think of a gradient of a function, right? What is a gradient of a function, right? You're taking a scalar and you turn it into a vector, right? So you have changed a scalar into a vector. which essentially is like looking at the 0, 0 tensor into a 0, 1 tensor.
Okay, I see, because I made a direction to it, which is another dimension.
Yes, yes. Maybe this is the simplest way of thinking of that. Right? Maybe it's not just a simple derivative. Well, it is a simple derivative, right? It's a derivative, but with respect to all coordinates.
Okay. Okay.
So analogy, the correct analogy might be to a gradient. But actually, I'm going to discuss, after we do all the math here, I will discuss this so you can see a lot of the theorems from vector analysis, you'll get it for free after we do all the hard work. So it's not really free. You have to do the hard work first. Okay. Yeah, maybe this is the easiest. You can think of it in terms of the way you think of, it's really a vector analysis, right? So a gradient takes a scalar, turns it into one form, essentially. Okay. Covariant derivative of covariant vectors. So again, we have the transformation laws of covariant vectors, right? Transformation law of covariant vector. Omega mu prime dx mu over dx mu prime omega mu. Again, we want to take the differentiation. D omega mu prime over dx mu prime. Again, similar to what we did, so I'm going to do it slightly faster. It's dx rho over dx mu prime, dx sigma over dx mu prime, d omega rho over dx sigma. So this is basically this is the second term, plus d squared x rho over dx mu prime, dx mu prime omega rho. Should have written it all here. Fix it to make it easier. Right. So again, we take omega, we multiply it with this transformation law of the affine connection. But now we don't need to do, just going to use this equation here. What's this one here? Right. So use that and multiply that by omega lambda prime. So gamma lambda prime, mu prime, omega lambda prime is dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime, gamma rho tau sigma plus dx lambda prime over dx rho, d squared x rho over dx mu prime, and then omega lambda prime, I can just write it as dx kappa d x lambda prime omega kappa. So again, this is dx sigma over dx. Again, I'm using here a delta function, right? This is a delta function, and this is a delta function. Right? So I have a dx sigma over dx mu prime, dx tau over dx mu prime, and This is a delta function, so it's just gamma. It's a delta kappa rho, so I can put it as a gamma kappa tau sigma omega kappa. And then for the second part, we have plus what's written here, d squared x rho over d x nu prime dx nu prime. We have a delta, again, kappa rho, so I can switch rho to kappa. Omega kappa. Okay, again, I have that equation and I have that equation, so I just need now to subtract them. And so d omega mu prime over dx nu prime minus gamma lambda prime nu prime omega lambda prime is just dx rho over dx mu prime dx sigma over dx nu prime. I see that I switched tau with a rho. It's kind of annoying to take care of all these dummy indices, but it's really nothing but taking care of dummy indexes. So don't pay. I mean, okay, you do have to pay careful attention to what I'm doing here, so that you see that I don't cheat you. But I told you I can get confused with no more than that. I just have to do it slowly. Times d omega rho over dx sigma minus gamma kappa rho sigma omega kappa. The last term just vanished. So again, this is essentially what we wanted. So we define a covariant derivative for a covariant vector. Again, nabla lambda omega mu is just omega mu semicolon lambda, which is just the regular derivative d omega mu over dx lambda. But now we have a minus sign. Gamma, again, the upper index is a dummy index, and the lower two index are mu and lambda. The order doesn't matter because the affine connection is symmetric, right? Times omega sigma. And this equation here specifies that this is a tensor, right? Because omega mu prime lambda prime is just dx rho over dx mu prime dx sigma over dx nu prime times omega rho sigma. This is a 0-2 tensor. Which is what we wanted. We got into an operator. We find an operator that, again, reduces to the regular partial derivative in flat space-time, but transforms like a tensor. Or not but, and transforms like a tensor. Okay? Now, the generalization to any tensor, of course, is now straightforward, right? For each upper index, right, I'm going to get an extra factor of plus gamma. And for each lower index, I'm going to add up for any extra factor with a minus gamma, right? So generalization to tensors of arbitrary rank is straightforward. Right. T mu1, mu2, mu1, sigma, right, is what? So we start with a regular derivative. So this will be dt mu1, mu2, mu1 over b at sigma. Now we said that for every upper index, we have a plus gamma. For every lower index, we have a minus gamma. So the gamma would be plus gamma. We take the index, mu1, right? And then the lower index will be sigma and the dummy index, lambda. Multiply by the tensor with the dummy index, lambda, replacing the index that we were using for the gamma, right? And then mu2, mu1. Now we have to add up another term for the second index, plus gamma mu2, right? Sigma lambda t mu1 lambda mu1 lambda mu1. It will be the last term that I put in.
With a minus?
It's a minus, right? What's going to be there?
Gamma.
Gamma. What will be the indexes in the gamma?
Dummy index sigma, I think.
So the down index will be sigma. What will be the second down index?
Gamma, I think. No, new one.
New one, that's right. What is the upper index?
Another dummy index.
Dummy index, that's right. And then what am I going to multiply it with?
T mu1, mu2 times
No time.
gamma.
And the lower index is the dummy index. Okay, so this is how I take a covariant derivative of a tensor. And I can easily generalize that to any tensor. Okay. Questions? Again, I told you it's a bit ugly, but it's really math. It's really algebra. It's not just math. It's really algebra. Just keeping traces of all these indices, but no more than that. And the result is extremely important. Right, because by doing that, we were really able to extend the concept of partial derivative from flat space-time to curved space-time. And this is an essential part in writing any equation that describes the physics, right? Of course, we did it in a general way. We did not use any specific coordinate system, right? Now, let me put a few more comments about covariant derivative. Any further questions before I put in the comments? No? Importance of covariant derivative. Okay, so covariant derivatives, the way we wrote them down, right? It's pretty straightforward to show, right? They're linear. Right, so alpha t plus beta s, t and s are two arbitrary tensors, right? Covariant derivative with lambda is just alpha t lambda plus beta s lambda, right? Alpha and beta are numbers, and t and s are tensors, right? They obey the Leibniz rule. Right. So the covariant derivative of an external product of t and s, which is just the covariant derivative of t times S plus T multiplied by the covariant derivative of S. If you want Ts lambda, it's just T lambda S plus T S lambda. What's the covariant derivative of the metric? What is the covariant derivative of the metric? Three minutes ago, I asked you if you have any questions. Well, some help? I can wait.
Maybe it's just the differentiation of the matrix.
It's a what?
Just the differentiation of the matrix.
Yeah, which is equal to what?
G mu nu over x gamma.
We can write it down, right? dg mu nu over dx lambda, right? But now we have minus, right? Gamma, what would be? Rho,
Yes.
lambda mu, g rho mu minus gamma rho lambda mu, g rho mu.
And the multiplication of the gamma and the g doesn't give a delta?
Give a what?
Gives a delta because gamma is defined as half of
Their delta function because the gamma is defined as the inverse of the metric. You're right. And then
stuff
Then
cancel out.
yeah, everything is vanished.
it's vanished. Yes, this is 0. Why is this 0? This is equal to 0. Why is that equal to 0? You can work the hard way and show it, but there is a simpler way of showing it. Why it is equal to 0?
Because the transformation laws has given us a gamma mu nu here with the upper indices. It gives
No,
no.
no, 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 no. Still don't see it. Why is it 0? What am I doing here? That's important. Why am I doing all that?
Maybe the metric is constant over the
How did we start this whole story? Why am I doing what I'm doing? Spending our time
you're deriving the metric which represent the curved space with direction of the curve. So I think the metric is constant over the curve, so the derivative will be 0.
You're close, but there is a simpler way of showing that, much simpler. But remember, what did we say, right? We can always erect a flat space-time, right? Coordinates, right? Now, in flat spaces, how does the metric look like?
It's a constant.
Oh,
Right.
then the derivative is 0 and you can transform it. In 0, it stays 0, right?
Thank you, right? So in flat space, right? In flat space, right? Right, G mu nu turns into eta mu nu. Right, eta mu nu is just the metric in flat space. Now, since it's flat, right, then the derivative is 0. Eta mu nu lambda. I'll write it automatically, by the way. Is 0, right? But this is a tensorial equation. And what did we say about tensorial equations? They are true in any arbitrary coordinate system. So if it's true in one coordinate system, it's true in any other coordinate system, provided the equation conserves its form. This is the principle of general covariance, right? That's what I started with, right? So since this is 0, that means that G mu nu is 0. Now you can do it. You solve it so that it's 0. You know what is the definition of eta, of gamma, sorry. The affine connection.
Did you mean it to write comma becomes semicolon?
Doesn't matter, right? In flat spaces, it doesn't matter, right? Because the affine connection is 0. Right? Is that what you asked?
Yeah.
Yeah. Okay. Now this has a name. What is called the metric compatibility. It's really called the affine connection compatible with the metric, but the other way of writing it is it's called the metric compatibility condition. So it's just right, metric compatibility. Compatibility. I'll use it down the line when we will analyze trajectories of particles in curved spaces. So, again, right? This is a tensorial, this is true, and this is a tensorial equation. So true in any frame due to principle of general covariance. So, again, the importance of this covariant derivative is that one, it converts tensors to other tensors. So we're working with tensors, which is what we wanted. And it reduces to the ordinary differentiation in the absence of gravity, right? When the affine connection is zero. So given that, we now have a prescription or an algorithm, right? To write down the effect of gravitation on any arbitrary system, right? What do we do? So to assess the effect of gravitation on arbitrary physical system, right? We do two things. The first thing is that we write an equation, right, in SR, which holds in the absence of gravity. We write an equation that is true in SR, no gravity, right? SR is special relativity. And then every time we see an equation eta mu nu, right, replace it with a g mu nu. Every time we see a derivative, replace it with a covariant derivative. That's called the comma, semicolon, comma rule. derivative goes to covariant derivative. And according to the principle of general covariance, we know that the equation we obtain will be correct in the presence of gravity. Aha. Cool, isn't it? Very cool. Yeah.
Is this why we worked so hard on writing special relativity with tensors and vectors? So we can generalize it now?
Exactly. Exactly. And we did not waste our time doing special relativity. Everything we did in special relativity, now I show you. This is everything you need to do to generalize it to general relativity, and you know that the equation you get is going to be correct.
Like equivalence in general in special relativity to work in rest frame and then move to more difficult frame via Lorentz. So now we are working in, in easier frame and then move it with the, because it's a sensorial equation.
Yes, you can think of it like that, but I told you, now it's much more general because now we work in any arbitrary frame. Lorentz transformation essentially takes you from one inertial frame to another inertial frame. Now we're not assuming that the frames are inertial because they are not. Okay, guys. I told you it's really cool, but I told you it's not going to be so easy. Do yourself again a big favor. Review this material. It's not hard, but there are a lot of subtle points here which you can easily get lost. Especially getting lost in the math and getting lost by seeing all these maths and not seeing the physical picture. So make sure that the math is clear to you, that you see that everything that I did legally, and I did not trick you, and I did not make any mistake there in the indices, the mu and u, because I had to switch indices at certain points. This is just because when I wrote them down initially, I just wrote the mu and u, and then okay, I made some mess there, but the mess was fine. So check out that it's all working out properly, and so that you'll be ready for the next lecture. Okay? Have a good weekend, guys. Question before we go? Yes, please.
I have a question according to the Levitzivita.
Yes.
And we multiply by the sign of G because we are changing the lower indices to the upper indices, and every time we get a -1.
Yes.
Okay. Thank you very much.
Okay. Now, I did not give you the full proof of that because you can find it in first or second year linear algebra textbook when you deal with Levitzivita. If you really insist, I can tell you which book, but I know some books in English. I'm not sure I know the books in Hebrew. So you can find it, right? Or just Google it. And you'll find it there as well, I'm pretty sure. Any further questions? No? So have a good weekend. Enjoy it. And I'll see you all on Sunday.
Thanks. Bye-bye.
Bye-bye.
Bye.
Have a good week.
Bye.